Okay, we're recording. I'm about to share my desktop.
Mm-hmm.
Okay, so can you confirm that you can see my desktop?
Yes, I see the window.
Okay, excellent. So welcome to the fourth session. I apologize again for missing last week's or postponing last week's session. That was unfortunate. We'll continue where we left off with input and output today. Any questions on the exercises?
I was behind, like I told you in the message, so I need to check for some of them. But I have been doing, and it's very interesting. So I have tried. Even my husband is a programmer, so he has solved some questions that I had.
So you got some extra help. Well, that's good.
Yeah, of course.
Yeah.
It's really useful.
Okay. All right. Well, keep trying, and if you have any specific questions, let me know. The solutions are now posted, so you can always compare what you're doing with the solutions online. Let me just go right ahead. I think most people for today are going to be looking at this video later rather than join online, but we'll keep an eye on the participant list here. Okay, let me see if I can make this full screen. I did, but it disappeared. Okay, so we're going to have to use this. Okay, so today's topics, continue reading from text files. We're also going to discuss writing to text files, and we're going to try try how to do some debugging and problem solving using the try and except blocks. This is really useful if you have any inkling or if you suspect that the code might break. You want to capture it. And then finally, we're going to talk about functions and libraries. That's one of the key components of programming, particularly in Python. Well, in any programming language, functions should be thought of as the atomic level of programming. They usually do one thing, and you string a bunch of functions together to create a whole program. Okay, so let's continue with input. Input. So again, we're going to focus on ASCII. So these are files that you can create using any text editors. These are files that you can download, say, from IPAC, if you're working on WISE, 2Mass, any of those data sets. And these are not the same as images. Images tend to be binary files. So if you're working with FITS files or JPEGs or PNGs, we're not going to cover that, at least not in this tutorial today. If there is time next week, we might talk about using the Python imaging library to read different types of image data and also FITS images. Okay, now with everything else in Python, the bare bones that you get with Python by itself is okay, but not great and not as easy to work with when it comes to reading data from files. So of course, a lot of programmers over the course of years have developed libraries, and some of those are included in NumPy, but there are additional libraries, and we're going to touch on one of them in particular today. And those libraries make it a lot easier to read data into arrays or data sets or data columns and work with it using NumPy. Okay, so I will introduce the bare bones Python way of reading the data, and then we're going to say goodbye to it unless we really want to stick at that low level for some reason and switch to NumPy's way of reading data. And then the AstroPy library. Okay, so we talked about this last week as well. You can specify a file and go through some commands, particularly open and close, to connect the file to your programming session. Once it's connected, you can read individual lines in it. These lines are read as string characters, one at a time, or if you say read lines, it would read the entire file for you. That's not good enough if you have a data table, because now what it's done is read each row as a string containing numbers. You would then have to actually parse the data yourself, split it into individual columns, and then populate it. But let's take a detailed look at what just happened in that basic code. First, we have this command file equals a string. The string variable file is basically a holder for whatever your file name happens to be. And it's a .text file, but it could be .dat, .table. It really doesn't matter what the extension is. What really matters is the content. Now, if you don't tell Python where this file is kept, here I've told it that it's in my home directory, and this is what the Mac OS will have for home directory, then it's going to look for it in the current working directory, which is wherever you started Python from. Since you may not know where exactly it thinks it is, and unless you set it, I would say it's a good practice to always give the full path name. Okay, or you can split it like I have done below. So you can have the directory name to be whatever your working directory is, and then you always attach it with your file name. So JBand photometry, KBand photometry are two different files, same directory. You can specify them and access them this way. This is just programming style. You can follow your own preference, your own instincts, and your own style and organization. Okay. Now the next command that we had was the open command. Open does exactly, it's a function, it's a basic core function of Python, and open means that connect this file, which is on your hard disk, to my programming, to my live programming session in Python. And you can make that connection in a bunch of different ways. Okay. First of all, obviously you'll need to tell it what the file is. So this is the full file name, including path. If you give it a file name and the file name doesn't exist, Python's going to give you an error message, and it's going to make noise about it. The next argument here is more interesting. And notice I have quotes and R and then end quotes. Whatever this next argument is, it should always be in quotes, and because it's going to be a string. And then depending on the value of the string, Python would connect to it in different ways. Okay, R is for read only. If you read, you can't write to this file. If you do a W, you can write to this file and you can read from this file. If you do an A, you tell the Python that this file should already exist, and I'm only going to add some more data lines to it. Okay. Now, once you've opened this, notice all of this is set equal to another variable, and I happen to call it OU. You can call it anything you like: my input file, my connection, input source. But the point is that whatever you call it, from there on in your Python code, that is your handle into the file. So if you're going to write to this file, you're going to send the output to OU. Or if you're going to read from it, you're going to work with this thing called OU. Moving on. Now, the next thing we did was to issue a line command. Let me go back. I didn't repeat it in my later slides, so I'll just say it here. Now, as I mentioned, OU, the variable OU, is our link to the opened file. And OU provides a bunch of utilities now, and the first one is read line. So OU.read line will read the first line in the file. Okay. So you've read the line. The variable line now contains the first line in the file. So notice as you're moving along in these tutorials, the variable names I'm choosing are more or less correspond to what the value that they contain. Just to remind myself what it is that I'm dealing with. So if I have line, I can do many things with it. Line is now a variable, and this variable allows me access to other functions that are associated with it. So one of the more useful one is line.strip, and what it does is it strips the trailing control carriage that is usually invisible to you. But that's definitely part of your data files. If you don't do that, then Python might end up putting in a double end of line character, so you may get extra lines where you don't want it. So it's a good practice, at least I find it a good practice to take that out with the .strip command. It would also take away any of the trailing or leading spaces. So unless they're significant, you usually don't want them. Line.split would allow you to split the individual elements of the line. So for example, if I had 1, 2, 3, 4 columns in my data file, the first time I read that data, it's going to be a character variable with 100, 34.2345, -5, whatever, and then 1. This is all a string. If I print line, this is what I'm going to get. If I split it and give it no argument inside the split, it would use space to make the split. So then it would give me 4 characters, 100, 34.2345, -5, and 1. Okay, so now this is a string array. Each one of them is split according to whatever separator I use. I can switch, and if it's a comma separated file, I can ask it to split using a comma. Okay, and that's what the argument here is specifying. But the point is that you can then split it. Once you've split it, then you can actually play with it. You can convert these numbers into their intended formats like integers or floating points using yet another operation on the split. But this is the hard way of doing. This is sort of reinventing the wheel every time. If you want more information on it, there is this website that I have marked here. We can take a quick look since on this side. Oops. That's interesting. Okay, something for me to follow up on to see if this somehow got moved. It didn't. Okay. So I would leave that to you. This is a useful help page. You can do it many different ways. Here, for example, is another way that this person has read the data, including header lines, and then gone through each one of them and parsed them through. Okay, so good tutorials here. But we're going to move on. I guess I have my own tutorial following here. I will let you look at this yourself and maybe even play with it. And here's the complete set of commands that you can put in a script that will do the splitting and create 4 different columns. Okay, but we're going to move on to using NumPy, and that's a much better way of addressing the data. And here's why. You don't have to worry about opening, attaching, and doing any of those things. The data format is not as good as I would like, but it's quite a step above the low level. Okay, so if you have a set of data and you wanted to use NumPy, NumPy gives you a function called gen from text, generate from text. That's I think what the intended long description for this function is. We import NumPy before we begin, as usual, and our handle np gives us access to every single function that is part of the NumPy library. And then using that handle, we access now generate from text. My file, in this case, is equivalent to file1, whatever the variable is that is pointing to your disk. But notice now there's a few other arguments, okay? And these arguments are where the power of using gen from text comes from. You don't have to worry about opening, closing, reading each line, parsing each line, setting it equal to a variable and appending it and keep doing it over and over until you're done, okay? NumPy gen from text will do that for you, but it does need to know a priori what to expect in the data. So the data type, dtype, if you use NumPy a lot, that's a name that you should become familiar with, dtype. So the dtype is now a Python tuple. That's what the parentheses are. And it's telling it that I have an integer, a float, a float, a float, and then a string that's 20 characters wide in my data file. Okay, I hope you excuse the background noise. Those would be my colleagues down the hall. Names equal ID, RA, dec, flux, and a comment. So in this file, I happen to know that the first column is an ID, then the second 2 columns are the positions, right ascension and declination. The third column is the flux for a star, and the fourth comment is a comment. Fifth one is a comment that tells me that something about the star, such as be careful, this one is a binary, or we got this from somebody else, whatever the comment may be. And we're allowing 20, we could allow anything else we want. Skip header means that I expect the first 3 lines to not be data lines, so don't worry about them, just skip them. Okay. If you have more than the 1, 2, 3, 4, 5 columns that we had in the file, then you can specify which of the columns are relevant and correspond to the values that I'm talking about here, ID, RA, DAC, flux, comment. And finally, there's a delimiter, which is normally taken to be space, but if you have comma, tabs, anything else, you can specify it with this particular keyword. Okay, so this construct is sort of the Swiss Army knife that you can unfold and get and define all the columns, assign them names, tell it how many lines to skip, and then which of the columns to read. Okay. Notice this is Python, so you would be stuck using starting with 0 instead of 1, which is where when I first started programming, that's where I thought everything should start with 1. But it doesn't. You just have to get used to the fact that most programming languages start with 0. Okay, so this replaces all of these things that we do before. We open, We read individual header lines. We define our columns. Okay. We read individual lines. We repeat this until we're out of lines, and every time we read a line, we parse it, we split it, change it to integer, float, whatever we think is appropriate, append it to our variable, and finally close it. Replace all that with a single line. So that's the advantage, and that's really the power of this method. So, any questions so far? Okay, so here is a reminder of what the various arguments are to this, and you're just going to have to try it to get used to it. The output is a data structure, and you can access individual elements of it by the name that you assigned it. So for example, we read ID, RA, DAC, flux, and comments. So if you recall that we set the whole function equal to the variable data, okay? So this variable data now contains every single one of your columns. Okay, it's defined the way you've defined it, so integer, float, whatever you called it. When you access the individual columns, data ID, this is now a vector, and you can access individual elements of the vector the same way you would access any other vector in Python. So 0 is the first element, 0 through 2 is the first two element. This is a silly way of writing all of the elements, and it's equivalent to not specifying it and getting all of the elements. Okay. Okay. If you didn't give it names, if you decided that that wasn't, you forgot, or if you decided that that wasn't necessary, in other words, you skipped this part, then what happens is that all of your column numbers are going to be called, given a prefix f and then the number. So it'd be f0, f1, f2, f3, f4 in our case. Okay. So data ID would not be there. It would be data f0 if you didn't give it the names. Okay. A couple of other useful things that you can do with gen from text, which are optional. You can also say, instead of saying that, I have skip header, number of lines, you can say that throughout the file, I use the pound character as my comment. So every time you encounter pound, you can just skip it. Don't worry about it. Okay. And comment equals pound tells numpy that that's whatever, that's the character. The big start, if the line starts with that, just a comment. That's just for me. That's not the data. Okay. That's useful if you want to edit data. You can always hide it from reading into your Python session by putting a comment. It's also, so I would always say that if you're making text files, data files, get in the habit of using comments characters to hide your comments from reading. It makes it easy to organize, and then furthermore, you don't have to worry about counting how many header lines I have or not. Okay, auto strip equals 0, auto strip equals 1 is basically 0 is false, 1 is true. You can also think of it as off. You can think of this as on, and that's to remove the white spaces from. That's just spaces from the text file. Automatically, just get rid of them, the leading and the trailing spaces. Skip footer works very much like skip header, except at the end of your file, if you've got some footnotes that are not part of your data, you can use skip footer, or also you can hide them using the comment character. Okay, so this provides a fairly powerful way of accessing data file. And it's also fairly generic, down to where if you've got 30 columns and you're only interested in 4 of them, well, here's a way you can get to it. Okay, it's in fact, in some cases, you can also get the names automatically from the file. I will skip that for now. Okay, so output is about as easy as input. Let's talk about the basic Python way of doing the output. We have already met print. If you say print and then hello world, it will print it to your screen. All you have to do is redirect that to your open file, and the same thing would appear in your file instead. Okay, so just like with our input code, we define a variable. This variable connects us to our file. Okay, then we use the open statement, and this time we're going to use W, which means we're going to use it to write to this file. And then modify the print statement by adding 2 greater than signs without any space, and then this handle for the file. So here is OU and hello file. If you execute this line, you will not see anything on screen. This output is gone to the file. And when you close it, Python would actually close this file. Then you can go outside of Python, bring up your favorite text editor, and you'll see that in this file, output.txt, there is a single line that says hello file on it. Okay. So this is where the trailing carriage return becomes an issue. If hello file was something that I had read from a different file and I'm now writing to output.txt, if I had not used line.strip, it would have that extra carriage return, and then the print statement would automatically insert a carriage return, thinking that that's what you want for the most part. So you would end up with an extra line, extra carriage return, empty line in your data file. Okay. If it sounds confusing, it really isn't. It's just you get used to it. Just do it a couple of times, and then you'll know what to expect, and it becomes second nature. Okay, moving on. The next couple of slides will provide a bit more detailed look. I think I've done the explanation, so there's not much I can add. Again, you have to be careful. This is part of your organization to point to the right directories in the file names. Okay. And a reminder that you can also use A instead of W to append. So when you issue the print statement, hello file, in that case, it would go automatically to the end of the file and add the hello file there. Okay, then here's our write statement again. Right, so now remember last time we also covered formatted output. The only thing that's different between the normal print statement and this print statement is the addition of that little syntax here that tells Python to send the output to my output unit here instead of to the screen. If you had a formatted write statement, then that's formatting rules will still be applied. So you would get a formatted output in your file. And here's an example of a formatted output. Okay. In this case, I'm writing a header line, a second header line, a header line, and then the data that I read from last time, I'm now writing it in a slightly different format. Okay. So here's data ID I. So I ranges from all the lines that I have in my data. So again, if you are going to use the primitive Python module for accessing the input and output, you have to basically go through it one by one through each line. And again, as with the generate from text, NumPy provides us with a single line equivalent, which is save text, obviously. You give it the output file name, you give it your data vector. Notice in this case that you have just provided the variable data. You don't have to go through it. You don't have to parse individual elements of it. And then you've supplied a format statement here. You've also supplied a delimiter if you want to use something other than white space, and then a series of headers separated by carriage return if there's multiple line. Okay, comments if you want any comments, and those are going to go with your headers if you supply them. Okay, so that's a lot easier than what you've seen with this one here. Okay, and that's the whole power and utility of using a library. So people just really get sick of doing this over and over, so they write a function, save text, that does all of that for them. It makes this nice print statement. So this print statement would be echoed pretty much like this statement somewhere in save text code. Any question on either input or output?
No, it's okay, thank you.
Okay, good. All right, so now I promised the try and except block, and that's really useful for catching errors, or when you're not sure that the code would behave well in one way or another. You also can use it to make your code more robust, for example. So if for example, you're writing a code that creates a function, and one of the things you supply to that function is a file name, and the file name is supplied by user or by you or read from somewhere, and you're not sure that they would be supplied correctly, and try and open and manipulate this file, you would end up with an error. So every time there's a chance of an error that you can't program, you can try and use the try and except block here. Okay, and here's how that works. It's just like an if-then statement. You say try colon. Remember, colon is fairly universally used in Python to designate the end of a particular control command. Here it's try. When we had if or when we had for, they also ended with a colon. So try, and then here's your set of commands. So they could be, for example, save text or something. Try this. If it works, good. If it doesn't work, then you get something called an exception. An exception is computer lingo for error. So when an exception occurs, except exception E, that's just the syntax, and we'll get to talk about it a little bit more. Do the following statements. Okay, so try my commands. If they work, do nothing, just execute the commands and move on. If they don't work, catch the exception. Okay, put it in a variable called E. Once you've caught it in E, you can do various things with it. For example, you can say print e.message, and it will tell you what the error actually is. At least what Python will tell you what it is. Most of the time, there's a second set of commands there that are executed. But if these command 1, command 2, if this block was absolutely essential for your code, then at this point you might want to stop all function and say print error, I cannot go any further. Here's the error message from Python. Okay. So this is a way to make your code safe from bugs, from unintentional dropouts and errors. But when you use try and except, you actually do slow your code down. That's the only drawback. Otherwise, you could have a try and except with every single command. but that would make your code very slow. So you always strive for making a robust code that doesn't need the try and except, but where it becomes iffy or where you're not sure, then you can implement the try and except, and it gives you more control over what to do in case a file isn't found or the format isn't what you expected it to be. Okay. Don't expect miracles from e.message. Okay. They tend to be fairly basic, such as file not found or incompatible types. So file not found is more useful, tells you that whatever you supplied it isn't any good. You can create code that will print things like, this is the file you tried to access in command 1. This is how I understand the name to be. And then that's one way for you to debug to see if you supplied the correct file name. But e.message, when it says things like incompatible array types, is a lot more frustrating to understand. It probably tried to parse a statement like this and tried to match, integer format 4i with maybe a character one, and if that mismatch ended up somewhere in that statement, it will tell you what it is. It won't actually give you such detailed information like ID that you're trying to write is a string, not an integer. Okay, that would be very useful, but those commands, you don't get that kind of detailed help here. Okay, the last thing that I'm going to cover, but first, are any questions on the try and the except?
No, Babar, thank you very much.
Okay, moving on to functions. So Margarita, you're on, and I think you're the only one who's on. I got a bunch of emails that people are going to be watching the video. So I'm speaking as if I'm talking to a live audience, but it's I guess for the benefit of those who will be watching this video later. Okay, so let's go on to functions. This is one of the core ideas behind programming that you should absolutely adapt, use all the time. Okay, make your own functional libraries, and that's when you start becoming a real programmer, so to speak. At least as said by me in some sort of a haughty manner, I guess. Okay. Functions, what do? They execute a set of instructions, okay, a basic code. You want to define the functions so they do one thing. They can do multiple things, but if you want to do multiple things, define multiple functions as a general rule of thumb. But depending on your need and what makes sense with your organization, maybe you do want the functions to do multiple things. But generally, they are written to do one thing and one thing only. And you string a whole bunch of these functions to create your program. Okay, what are the advantages of functions? Okay, sorry, it's all in here. The best thing that they provide is that if you're using the same code many times, then by defining of functions, you will tidy up your code. You would put it in one place, and then you would always call that function. You don't have to write this repeat, cut, and paste that same similar code all the time. If you have a special way of calculating, say, the average of a number of vectors through some weighting scheme that's partial to how you calculate it, function would let you define that, and then you supply your numbers to that function. It does the numerical calculations and sends you back the result. Okay, you can change it, the parameters to supply it a different set of numbers, but you don't have to repeat the code multiple times. the biggest advantage that gives you, apart from tidying the code up, is that there's only one place where you need to debug it. So if you have written the same code 10 times and cut and pasted it, okay, and you found a mistake, you'll have to modify it and find it and modify it everywhere where the original cut and paste happened. So avoid that. Use functions. And like I said, a set of these functions you can call a library. Okay. So how do you define a function? You use def. When Python encounters def, it's expecting the definition of a function. Okay. So the syntax is pretty easy. Def, whatever you want to call the function, and then in parentheses, arguments that are expected for this function. We'll come to some specific examples in a minute, so you can see how that works in reality, but I just want to give you the theory basis, the generic basis. There are two types of parameters that you can give to a function, and the function will expect either of them. You can also have a function that has no variable. So this thing, for example, could be a function that prints a particular message, and it always prints the same message when it's called, and it doesn't need to change any of the commands based on input that you supply. So in that case, there would be nothing inside these parentheses. All of these would be gone, and the parentheses would open and close. You do need that, and then you would follow that by the universal end of a definition of in Python, which is colon. Okay, but if you do have arguments, there are two types. There are those that are mandatory. The mandatory arguments don't have an equal to sign. Okay, they're simply the name of the variable, and that name of the variable would be set to whatever you supply to the function. If the mandatory arguments are missing when you call the function, you will get an error. Okay. The other type of variable or the parameter is the optional argument, and you can have as many mandatory and optional arguments as you like. In this case, there are three. What distinguishes an optional argument is the equal to sign. When you look at this definition, you know that these two are optional. This is mandatory. Okay. The equal to sign, what follows after that is the default value. So if the user does not specify, when he calls the function, it does not specify whatever this value is, then that value would be whatever the default value is. Okay. Let me step back to this one. This save text is a function. Okay. Notice that my output file, data, both, there are two arguments here that don't have an equal to value after them. These are mandatory, and obviously whoever wrote save text thought about it and said that these have to be mandatory. Okay, save text is expected to write some data to a file, so you have to tell it what the output file is, and you have to tell it what the data is. If you don't do that, then it wouldn't know where to write or what to write. Okay, so the coders of save text function made these two arguments to be mandatory. Everything else is an optional. If you don't supply a delimiter would be chosen for you. In this case, if in the definition of save text, it is delimiter equals a spacebar. If you don't supply a format statement is constructed for you, and it's always equal to floating point. I think that's the default. If you don't supply it a header, then the header lines are empty. Same with comments, they're not used. Okay. In the definition of save text, this is where the coders specified those optional arguments, and this is where the coders left the mandatory arguments. So the rest of the function is a series of commands that you want the function to do. Notice we're back to indentation. Python is very big on indentation, and I realize that we've gone a couple of days now without, or a couple of weeks now without talking about Python, so you may have to remind yourself that indentations are what you use after if, then, while, for, any of those blocks. Same with function. Everything that's indented is part of the function. Okay, once you remove the indentation, then the whatever it comes at that same level as the D, indented at the same place as the D, is not part of the function. The last command of the function is special. It's something called return, and then the result. Okay, result is simply a variable. Okay, it's not the actual result that's calculated in the function. I could have called it, foobar, for example. It's just the name of the variable. I just happen to call it result. Okay, and whatever is the value that's stored in result is sent back by the function. So if you're calculating the mean, you might want to call it to return my mean value. Okay, and my mean value is the variable that is connected to the actual memory in the back of your computer, the spot where it contains numerical character, whatever value it is, or an array. That's the handle into your memory. That's your variable. That's what's sent back by this function. You can also have a function that just has return without anything after it, in which case the function does a bunch of things and it never does return anything. Okay, it's rare, but you could have it. Usually, even if the function does a bunch of commands without sending anything back, usually I send return a status. So status could be OK or 1 or 2. So I know that everything that happened went without a hitch. Okay. Any questions so far?
No yet. I think it's clear. Thank you.
Okay, so moving on. Here is now an actual example. So this is a kind of a calculator. My math tool is what I want to call it. So I start off with DEF. As soon as I say DEF, Python starts listening for a definition of a function. My math tool, that's what I'm going to call it. And then the parentheses. Within parentheses, I want two mandatory variables, A, B. And I want one optional variable, and it's going to be a string with a single character, and then a colon that tells me that here I'm done with the preamble to defining this function. Indent, if operation is equal, meaning if that's what it's equal to, plus, then add A and B and call it result. Okay, else if operation is minus, subtract. Else if operation is in star, multiplication, then multiply them. If it's division, aha, now I can do something more fancy. If B is not equal to 0, result is equal to A minus B. I don't know why I did that. Else, it should be A slash B. Sorry, this is a mistake. That should be A slash B. Or print a message that says, I will not divide by 0. You should know better. You can make it whatever message you want. Return value is 0 itself. So here's result is then set to 0. If operation doesn't match any of these, so here's our final else, then you can say whatever operation you specified is not understood, plus operation. Okay, return value 0, result is 0. Then the final statement, return my result. So depending on what you supplied, you added, subtracted, divided really here as well, multiplied, or in the case of catching a couple of errors, set it to 0, and return that value in result. So the result got set as a consequence of one of these if then else statements. Okay. Now here's so this is now expecting A and B to be numbers. If you didn't supply numbers for A and B, then you will start getting into problems. Okay. And you might end up getting into errors. We won't go into that, but this is the sort of thing that you have to think about when you want to make programming more robust. Okay, this is just a simple example. We don't do a lot of checking here, but obviously before any of these operation blocks even begin, I can test whether A is a number or not, and I can similarly test if B is a number or not. And if they're not, then I return 0, which maybe that's what I want to return with a print statement. Okay, so in Python, you can, in Spider, you can define it. I'm going to leave it to you to actually type this in and then try it. When you want to call your function, you simply call its name and supply it the operation and the arguments. This statement, the first one, will simply print the results. The second statement will not print the result. It will do the multiplication, then set it equal to the variable C. Okay?
Yeah, okay.
All right, and then we're 6 minutes from the end. Let me briefly talk about the IPAC tables. We may have to pick this up again next week. So we're familiar, I think most of you guys that are part of NITARP, and even some of you who are not part of NITARP, if you work with 2MAS, if you work with WISE, then you have seen this format files. This should look familiar. This is a dump from a WISE catalog, and I actually have included it on our web page. That's this file right here. This is what it looks like. Okay, this is one that you can play with using this particular demo script that I will leave it to you. We'll discuss it now and we'll come back to it. This is one of the things that most NITARP folks have asked about using programming. So right now we're going to worry about just reading it. Next week we're actually going to manipulate it and then do things like make color plots. So how do we do it? My number one recommendation is to learn to use AstroPy, an ASCII table. So the reason you want to do that is because the IPAC ASCII file actually makes it very difficult to handle text. Let me explain why. Okay, first, there's comments. The comments are specified using the / character, and that would be fine if we can say comment equals, whatever it is, in our generate from text function in numpy. Okay, but then what happens is that we have a header lines in addition to comment lines that follow. And then each one of the columns is separated by a fixed width and not by a separator, a constant separator. And trust me, that's actually very difficult to parse, or not that easy to parse. And furthermore, you have nulls and other values that are not numeric. So if you're trying to write a code that parses each line and then asking it to convert numerical values into numerical values that are read as stringed into actual numerical values, when it encounters a null, it doesn't know what to do. You would have to put in a try except type of statement to catch that. It makes the code very messy. you're welcome to write your own low-level code, but all of those cases are handled by AstroPy. This is even better than gen from text. So for IPAC reading and working with IPAC type tables, I haven't found anything better here. It's still a bit kludgy, but it's a lot far less kludginess than any other way of reading IPAC tables in Python. Okay, you can go to this website and download it. I would recommend following their instructions. I think Anaconda actually includes it, so check that first. And if it's not included, then you can go and include it. You have a function called ASCII.read that will do all of the parsing and generating for you. Okay, so let me show that. I can't quite demo it. Let me just walk you through the code instead. And we'll do the demo. You can try the demo on your own. Okay. So let's make it big. Okay. This is now on the website, as is the table. And I'm using, first of all of the imports that I need to do at the very beginning. That's just a convention. Then I'm going to define a one-line function. Notice it's very, very simple. But I do want it this way because I want to be able to change it, maybe make it more complicated later. But this function, remember, is expecting one mandatory argument, which is the file name. Then it's going to call ASCII.read from the AstroPy library, and it's going to supply it a guess as to the format, which is ASCII.IPAC. And that's it. You don't have to do anything else. You can see that it's even simpler than using NumPy's gen from text. All right, so let's take a look. File name, I can call it into a variable file name, my big wise 2-mass or wise and 2-mass table. Then I use a variable called wdat, and I call read IPAC table, my function here, give it this file name, and magically wdat will now contain all of these numbers. Oops, I'm still demoing. Okay, so what can you do? Type wdat will tell you what kind of data it is. This is very useful, wdat.more. It would actually let you page through the data like you would a file. This only works on the latest versions of IPAC ASCII. So if you manage to get an older one, or if Anaconda has an older one, it may not work, but it would essentially show you this. Okay. You can also query what the length is. You can query what the names of the columns are, and the IPAC ASCII file has that information. So in this row, after all the comments are done, okay, it has designation, RA, DAC. These are the names of the columns, and these are the names that are going to be picked up by wdat using ASCII.read. Okay, so RA and DAC, for example, would be in there. You can print them just like using this construct. You can get the full list using call names function, column names. You can then extract them and manipulate them. Here, for example, W1M-Pro will give me the maximum value of W1M-Pro, which happens to be the wise W1 shortest wavelength magnitude. Okay, and then here's an example of how you can manipulate it further. I define an array of variables, and I define a simple for loop that gives me the range of values for each one of these columns. Okay, I will let you study that, and next week we are actually going to run this code, and then we'll do more than that. We'll try and manipulate it so we could do some plotting as well. Okay, any questions?
Maybe I will send you a message, Babar. Thank you.
Okay, no problem. All right, then I'm going to conclude sharing and screen flow capture. Goodbye, everyone.